So I think we should get started, if that's all right with everyone.
Yes.
Yep. Okay. Perfect. So welcome everyone. This is a session Advances in Macroeconomic Forecasting and Macroeconometrics. My name is Greg Ganich, and I'm the organizer of this session. And I would like to thank the conference organizers for including us in the program, and also the presenters for coming, and of course all of you for coming to this session. So without further ado, let's get started. Our first speaker is going to be Felix Kiesner. And Felix, you have 17 plus 3 minutes as we discussed. The floor is yours.
Thank you very much, Greg. Yeah, I'm Felix. I will present today first work, a little bit preliminary, joined with Matej Petrescu and Malte Knüppel, I guess, who is also here joining via remote. And the topic of today is to construct a test for testing correct calibration of predictive density. And what we're going to do is we extend basically the work of Diebold using PRT-based histograms to do so. All right, so again, what are we going to do? We would like to test whether the predictive density you have estimated really fits the data. And for this, we are going to use a PRT series. So what's PRT series? That's here basically the second equation. We simply use the value of the CDF of the realized value. And under the null distribution, or under the null, the PRT series should be uniformly distributed, and that's what we're gonna exploit here. And there are a couple of more tests which use these PRT series to test for correct calibration of the predicted density. One is due to Malte Knüppel again, which uses another transformation based on the PRT series that is a normal transformation, and then tests for certain moments of the normal distribution. And the other one, which is closely related to what I will present today, is one test from Rossi and Sarkisian, who basically use the Kolmogorov synonyms test. They also have in this paper another one based on Kramer-Vermeeses, so L2 statistic, but we're gonna exploit this one here, since they are also able to come up with nice confidence intervals for this test. All right, so why do we do this PRT transformation here and not simply run a simple test? The first one is basically instead of having different test statistics, we generate new data sets, right? So we always use these PRT transform. And what we have is a different PRT series for a different assumption. There's a first point. Second point is, of course, flexibility. We do not require that at all times we have the same predictive density. As you can see here, we may have different predictive densities for different points in time where we do the forecast. And what we're going to exploit there is just the PRT value for each of these. Another advantage of our approach is that we can get some clue what might have gone wrong simply by having a look at the histogram. All right, so what are we gonna do? Well, we simply construct now a histogram. These are the bins here. And if we do a one-step ahead forecast, we know that the PRT series, at least under the null, so of correct calibration, is not serially correlated. And what you can show that is that these bins there are jointly normal distributed, right? At least asymptotically. And that is what's actually done in the literature. So typically, there are many guys who use these PRT histograms, but either they will use just point-wise confidence bands within these PRT histograms, or they will just use uniform ones as suggested by Bonferroni. Okay, and that's also our first idea. So just have a look whether that actually works. So here I have one example how this looks like. So the null here is true. So just draw from the standard uniform distribution, and you can see here the Bonferroni bands. So joint bands. Okay, and the question is, we all know that Bonferroni is quite conservative, or might be quite conservative, whether we can do better here in this basic setup. And here in the next histogram, I hope that you can see that on the screen. So there are now 3 confidence bands here. The first one, the black one, also supposed to be black, is again Bonferroni as before. Then we have simulated ones from the multivariate normal distribution you can see here on the top. And we also have the exact simulated ones on the null. That is the green one. And I guess you can't distinguish the upper band here because they basically coincide. So Bonferroni is very close to the correct simulated ones. And for the lower band, we have that the correct simulated ones are a little bit larger than Bonferroni, but the difference is not too much. And because we basically discretize the lower band here, it might also be that that's the case why we observe this difference. So the difference is not really large. Okay, so what's also important to point out here is, although in this PRT series, we assume that the observations are not serial correlated, we have serial correlation in the histogram, right? And that is just due to the case that what we plot there are basically probabilities. So let's say if the probability of falling in the first bin increases somehow, then of course some of the other probabilities have to decrease. So by construction here, we have now serial correlation, and you can see that in the second line, the sigma matrix, the asymptotic covariance matrix of the bins is defective. So that's what we're going to exploit. What's also interesting here is we know for the optimal one-step ahead forecast that the correlation between bins is exactly -1/k. So if k gets large, here we have 10 bins. And you can see in this figure again that Bonferroni is quite close here for 10 bins to the exact simulated confidence bins. All right, so the interesting part is now what changes if we are not only interested in doing one-step ahead forecasts, but maybe two-step ahead or multi-step ahead forecasts. So that's one example. So we have a basic MA1 process. And if you use the conditional density, that's what we consider as correctly calibrated. That's the first histogram. Then the series is not correlated. The second one, if you instead for the one-step ahead forecast use the marginal density instead of the correctly calibrated one, the conditional, using all the information given your model and the data, then you can see here that in this realization, we're not able to reject using Bonferroni, but we get some idea here, and that's true for all models and DGPs we analyze. That is, if you have a look at the outer bins, that's first the last one, you get the impression that there is some more variation going on That's what we find, and that's quite interesting. So either if you are not using the correctly calibrated density, that is, for example, the marginal one for the one-step ahead, or if you do multi-step ahead forecasts, then we have increased variance in the outer bins. All right, so how can we basically address that? So our idea is based on the multivariate normal approximation here. And instead of knowing this covariance matrix sigma for the one-step ahead forecast, we do not know that if we do multi-step ahead forecast due to serial correlation in the PRT series, as well as the increased variance, at least in the outer bins, what we find empirically. So the strategy now is basically straightforward. We would like to use this multivariate normal distribution, and the only thing that we should do is estimate sigma somehow. Okay, so first, how can we exploit now this multivariate normal? And what we're going to do is we use so-called sub-T bands, for example, discussed in Montiel-Olaire and Blackbook-Miller. So if you have a look at the first equation there, that is now the test problem rephrased in terms of the confidence intervals, right? And that is, if you have a look here, that is so-called one parameter confidence band. So what we do not know yet is this parameter C. That's what we would like to estimate somehow. And mu, that is the expected value of each bin. That's what we know under the null, right? We know this should be standard uniform. So that is 1/k. And what we try to estimate are also these standard deviation of each bin sigma bi. So before, if you use Bonferroni, for example, we basically assume we have the same variance for each and all bins. And the only thing that changes is the significance level alpha here due to the Bonferroni inequality. Okay, so what are these sub-T bands now supposed to do? We basically transform the statistic. What we use is basic t-tests, so sigma I vi in absolute value, and we just take the supremum over all bits. And what, for example, Blockberg, Muller, and Olaire shown that these probabilities are the same. Okay, and what we're going to do now is we use that to simulate and find this quantile that is C. All right. So how does these sub-T bands look like? If we go back to our first example, that is doing one-step ahead forecast. So here, to my inability to draw in high-dimensional settings, I just use 2 bins. And what you can see here is the B1, B2 plane. And these rectangles here, these are the 95% confidence intervals or confidence sets implied by these methods. So the outer one, the green one, I hope that you can see that. This is the one implied by Bonferroni. And what we also see here is the sub-T bands. And the important part is we assume here we have high correlation between these bins, and then this set of sub-T bands is a little bit better. Okay, so how does it fit here? Well, again, if we have our one-step ahead forecast is virtually the same as Bonferroni or the correctly simulated ones. And what remains to be done is we have to estimate sigma somehow. Okay, and what we're going to do here is we do not simply use an HAC estimator to estimate this variance. Also, you can do that, but it turns out in our simulations that a strep or basically circular bootstrap is a little bit better. And to slightly use it, basically the best procedure we found here or analyzed, we use it per cent rank of the PITs, and in this way we basically enforce that the expected value of all bins is exactly 1/k. Okay, and how we gonna do that? We use the circular bootstrap. The block length of this circular bootstrap is estimated as suggested by Politis and White. And therefore, we simply construct now a bootstrap series of the bins and estimate the covariance matrix as such. So how does it look like? Again, for the MA1 series now, we do two-state ahead forecast. That is, we use a marginal distribution. That's the best we can do in this case. And you can see here that this confidence bands are basically fluctuating around the one suggested by Bonferroni. So there we don't or cannot improve much. If we would use an AR process with some persistence at least, then we see that the bands for the outer bands are much wider than the ones implied by Bonferroni. Okay, so one short empirical application, we use SPF. And we are gonna interested in the year-over-year growth rate of prices and outputs of inflation. And we assume a normal distribution. So we basically fit for the mean probability distribution forecast a normal distribution, and we use data starting at 81 to do so. Okay, and what we get for inflation are these two figures. On the left, you can see the nowcast, and on the right, you can see the one step ahead forecast series. And the solid red line, that is our expected value. And the black line are, again, the Bonferroni bands. And the red dashed line, these are the bands from our sub-T method. And the important part here is if you have a look at, again, at the one step ahead forecast series here. So it's quarterly survey. So we have some serial correlation, although we do one step ahead, so a year ahead forecasts, but we have a serial correlation for this reason. And as you can see here, if you would just use Bonferroni, these bands are not wide enough. So they are too narrow here, at least indicated by our method. And basically the same story is true for GDP growth. So again, if we have a look at the 1 year ahead forecasting series, you can see here that all the confidence band found by our method are outside the range of Bonferroni. So the basic idea to just use Bonferroni, although it claims to be uniformly confidence band, that's not enough. We have to take the serial correlation of the PIT series into account, for example, using the sub-T bands. Okay, so to sum up, basically the PIT-based histograms are a very easy method to check for correct calibration, but you have to be a little bit careful which confidence bands you use, and using these sub-T bands I presented today is a valid method, at least methodically, to come up with correct confidence bands. Okay, so that's it. Thank you very much, and I'm looking forward to any comments or questions.
I think we have time for a question. There is someone from the audience. So, if I understand correctly, that the longer the horizon, the more wide the bands are.
Yeah.
What's the maximum horizon that these bands may use? Like, if you do 2 year forecast, then
This depends on the DGP you analyze, and of course the distribution you have basically. So typically, if you don't have too much data, And then the lower band is not really informative. That's close to 0, but the upper band, well, this depends really on what you're analyzing. Yes. We have done many simulations, so for Arch, Garch, MA processes, and so on. But I can't remember what was the maximum value we found in all these simulations, but could be pretty wide. All right.
So let me just remind everyone that Felix is a student, and don't forget to vote for his presentation. So thanks a lot, Felix.
Thank you.
Our next presenter is Ludwig Florenz.
The clicker works?
Yes.
Control L, right?
Yeah.
Great. Okay, well, thanks to the organizers for including our paper in the program. I'm Florenz Odendahl. This is joint work with Greg, who's also here in the audience. Since we're both working at central banks, the usual disclaimer applies. This is our work, and necessarily it does not necessarily reflect the views of the Central Bank of Hungary, the Eurosystem, or the Bank of Spain. So this is work titled Reordering Variables in VARs with Stochastic Volatility, Implications for Forecasting and Structural Analysis. Now, let me start right away. So stochastic volatility vector autoregressions are kind of workhorse models for macroeconomic forecasting, as well as structural analysis. Now you would find certainly more than 100 papers that use this kind of models. And the most common specification is based on Primiceri and Coghlan and Sargent, which use a lower triangular decomposition of the covariance matrix. Okay, so we didn't try to get numbers, but I would guess that like 95% at least of all these papers that exist use exactly this algorithm to estimate these models. Now, importantly, this matrix reduction, so this lower triangular decomposition, is only meant to facilitate estimation of this model and is not supposed to embed any structural restrictions or assumptions in itself. That has the advantage that it makes it really easy to compute. So that both in terms of coding that you need to do, it's very easy to code it, as well as in terms of estimation types. No? So you can, in the end, use a simulation smoother because it's kind of, you can cast it in a linear form. Now, the drawback of this is that you end up with posterior distributions that are not invariant to the ordering of the variables. And then different orderings of the variables lead to potentially different conclusions. And important here, when I talk about orderings of the variables, that applies to reduced form parameters. Okay, it's not, here's nothing structural yet. Okay, this is really reduced form parameters. And well, this is really a property that you don't want, no, because you don't want to have different forecasts if you just change the order of the variables in your model. Now, what we're going to do in this paper is first we document this effect of different orderings that you see in this type of models. And we show, well, there are effects on both forecast and performance, as well as impulse response functions. And then what we also do is we provide evidence supporting an alternative ordering invariant stochastic volatility specification. Okay, so this is broadly the outline that you'll see. So what you'll see is some results regarding point 1 and then some results regarding point 2. Okay, very simple. So let me motivate, let me first give you a quick preview of results. So we find that ordering does matter, no? Otherwise I wouldn't be here. And then it matters for both point and density forecasts. And these differences are often significant. So they're reasonable in size, meaning that they matter, for instance, for if you want to do policy with these models. And there's no clear pattern. That's also important. No, it's not that always the first variable does best or something like this. No, that if you want to have the best forecast, you have to put the variable first. That's not the case. There's no clear pattern that we can find. And then that we find that this alternative stochastic volatility specification provides competitive forecast and it's ordering invariant. So you don't have this issue. And then what we have so far, which is going to be extended, but for now, what you will present is, so we identify a monetary policy shock with sign restrictions, and we find that, well, first, the IRFs look different for different orderings. And again, this alternative specification is kind of an IRF that's in the middle of all the other IRFs from the Primiceri specification, okay? So let me let me give you an illustration of this ordering problem. Let me start with a very simple VAR 0. Okay, so here VAR 0 means we have no legs because the legs here don't matter. This is an illustration. So what you have is you have these this vector of y's is equal to well, you have first this. Let me try to show it here. You have first this lower triangular matrix, typically called A, and then you have the diagonal matrix, which is lambda, and then you have the U's. The U's are standard normal. These here are the stochastic volatilities that are kind of moving here, so they follow here a random walk. Technically AR1, it doesn't matter. You also have that in alpha, time varying for simplification. It's not time varying here, but this is the specification that I would guess at least 95% of all, at least the vast majority of all people use this specification. And again, now this is this triangular lower triangular decomposition facilitated information. So the one step ahead conditional covariance matrix of this, what does it look like? It looks like this. That's a bit of a complicated expression perhaps, but in the end, if you look at the first diagonal element, you have this E of log lambda plus the eta. The eta is normal. So this first element is proportional to a log normal. You take the log, you have basically something like a constant plus a normal. The second diagonal element is the sum of two log normals. So it's not log normal anymore. Okay, and if you change the ordering of these two variables, obviously the distributions for these two variables for the variance covariance matrix changes. So there's no way how you can make sure that when you change the ordering, the posteriors here stay the same. To illustrate a bit how big this issue is, so what I'm showing here, or what we're showing here in this figure is for the case of n equal to 6, so with 6 variables, we show the exactly these diagonal elements implied by a prior, where we set the prior such that the priors on all these individual parameters here, the alphas, the etas, etc., they're all the same for all variables. And just by this triangular decomposition, what you see is that effectively the prior that you put on these variances, exactly on these diagonal elements of the variance covariance matrix, have very different both means as well as densities in general. Okay, so the points are the means of these distributions. So the further you go down in this ordering, the higher is the mean that you impose, and also the wider is the variance of this prior. And a similar picture emerges if you look not at the diagonal elements, but at the some of the off-diagonal elements. So what we're showing here is the last column of a variance covariance matrix, meaning the covariances of element 6 with all the others. And you see that the further you go down, the wider the prior gets. So in other words, the earlier the variable comes in this ordering, the tighter is your prior that this is centered around 0. And again, now this comes from priors that where you would think you impose the same prior on everything, but it's not the case. You really change the posterior distribution here with this. Now, related literature. Let me be quick with this. So we want to emphasize that Primitieri already acknowledged this problem. He mentions it, but he had the impression that it doesn't matter too much empirically. So there were no further investigations. Now, what you could do, of course, always is for say b bar of n variables, you could estimate all the possible different orderings, no? So this would be n factorial. The issue is that, even if you have just 6 variables, that would be 720 possible reorderings. This is not feasible. Now, for the sake of time, let me not go into all the alternative specifications and papers on this. Let me just say there are other papers that started to investigate this. This is rather recent that the literature has paid attention to it. They do all find that ordering matters. We differ typically in several dimensions. First, that we look at point and density forecasts, that we look at the structural implications, as well as the competitor model. Okay, if you have later further questions about other papers, the literature, I'm happy to answer them. Okay, so let me go into the methodology. As I said before, now this is the standard. The baseline model is this VAR with stochastic volatility with a p number of legs. As I said before, we have this lower triangular decomposition. Also, here we have this a to the power of -1 and the lambda that was before this diagonal matrix, and the A was this lower triangular matrix. Okay, this was what you saw in the illustration. As I said, lower triangular, diagonal, And here this follows an AR1. It doesn't matter, it can be an AR1 random walk. You can make the alpha time varying as well, which some papers do, only exacerbates the problem because you have more price and more variation. Yeah. And then what is the competitor model? The competitor model is an autoregressive inverse Wishart specification. So what is different here? So this ET, so let me maybe go quickly back. So again, here the ET follows this decomposition into a to the power of -1 times lambda times an error term. Okay. In the inverse Wishart, this is a bit different. In the inverse Wishart, there's no decomposition. In the inverse Wishart, you draw this sigma t, the variance covariance matrix, directly from an inverse Wishart distribution. Okay, now you have this kind of a bit, say, ugly expression here in the middle, which perhaps is a bit difficult to digest, but importantly, first thing to notice, there's no decomposition here. You draw directly from the inverse Wishart distribution. And why is it called autoregressive inverse Wishart? Look at this term here, you know, this is just scaling. If you look at this term C, kind of constant. And then, well, remember, this is a matrix, which is symmetric. So what you could do is, if you think about stacking just the lower triangular part of this, then you see, you know, just stacking the lower triangular part of this in this matrix, it has kind of a form of an VAR. So this is why it's called autoregressive inverse Wishart. Because, you know, these are matrices, you have this kind of matrix form here. But I think the equation hopefully is clear. You know, this is a kind to a VAR to VAR dynamics. Okay. Now the issue here is this cannot be cast in a linear Gaussian state space, so we have to estimate it with a particle Gibbs with ancestor sampling, which we also want to emphasize. We think that it hasn't been used much, and you know, the more complicated models get, the more you will need this technology, and we'll make some Julia code available to estimate this in really finite time, reasonable time. Greg, how am I doing on time? Okay, great. So let me go. So these are the two models. Yeah, we have the standard Primi-Cherry decomposition, and then we have this inverse Wishart. So let's move to some application data. Very, very standard data. We use quarterly US data from the FRED. The model has 6 variables. It's log of real GDP, the price index, the unemployment rate, then the log of PPI, then the Fed funds rates, and the term spread. So we try to put some real variables, some nominal variables, as well as some financial variables. Okay. And again, this is really not so specific to the variables that you choose. No, we have, for instance, we work on an application for the euro area, and the results are similar. The training sample for priors is 59 to 69, so 10 years of prior training. Again, this is not key to any of the results. Then we do a recursive estimation from the 70s. Sorry, the initial in sample is from the 70s to 98. And then we do recursive estimations from 98 to 2019 and produce out of sample forecasts. Here, these are pseudo out of sample forecasts because, well, we did not really care about real-time data here. Real-time data is not the point here. No? The point is that the ordering will matter whether you have real-time data or not. And then the evaluation period is 1999 to 2019. Okay, this is the data setup. And the leg length is equal to 4. Again, this is not key. No, it's just for your for completeness. Okay, let's look at what orderings we consider. So as I said, now the orderings will change the results. So what we try to do here is we just try to look at 5 different orderings. Okay, you know, again, now if you have 6 variables in the model, you have 720 possible orderings. So what we did is we specified something that we called a baseline ordering, which we thought most people would pick, which is ordering 1. So you would have GDP, PCE, unemployment, PPI, FFR, TSR. And then we have 4 other orderings that we drew randomly with MATLAB. So these are just reshufflings of the variables.
So TSP,
TSP is the term spread. So this is the difference between 10 years and 2 years. Well, now I'm not sure. Yeah, well, anyways, it's a term spread. No, exactly. So we have this baseline ordering and then the 4 others. Oh, okay. Let me quickly go to some results. So first, the relative forecast evaluation of the Primi-Cherry model itself. So what you see here are relative MSFEs or relative CRPS, depending on whether you're on the left or right side of the panel. So comparing the SV model of Primi-Cherry with itself, but a different ordering. So this is ordering 1 versus ordering 2. Okay. Values that are smaller than 1 indicate ordering 1 is better. Here, boldface means statistical significance. I'm not going to go into detail about the appropriateness of here the Debord-Mariano test, but think about look at the numbers. Now, what you see is these numbers are big, and this is not Monte Carlo uncertainty. No, we did this with a large. We did robustness checks using just ordering 1 with independent checks, and the results are literally 1. So this really comes from the ordering. No? And you have differences of up to 10%. So these are big, and they matter. And they're even sometimes bigger than 10%. You know, they get down to 17% because of different ordering in these variables. Now these are just like results concerning well, the pointer density forecast. What you can also look at is relative width of confidence intervals of these predictive intervals. Okay, so what we plot here are these relative width of always the smallest versus the biggest. And you see that these widths are typically like the relative width are around 80%. And for the FFR, this get down to really, really big differences now. And then, of course, it becomes clear this matters for policy as well, or it can matter for policy making, for instance. Okay, so I hope I convinced you that there are differences depending on the ordering. Now let's compare our invariance, our regressive inverse visual specification versus the Primi-Cherry version. What you see here are numbers of the comparison between the autoregressive inverse visual versus the SV. Numbers bigger than 1 means the triangular decomposition of Primi-Cherry does somewhat better. Smaller than 1 means the inverse visual. Now you see that mostly these numbers are around 1. For the density forecast, you see some results are better for the Primi-Cherry algorithm. For the FFR, the inverse visual does better. But our takeaway is really they're competitive. No, but they're very similar in terms of results. As you can see, most of these numbers are around 1. Okay, so you know this inverse visual is like a valid alternative specification to the lower triangular. And then let me quickly, how much time do I have left, Greg? 3 more minutes. 3 more minutes. Okay, so let me be really quick on some IRFs. Okay, I'm not going to go into detail how we identify them with sign restrictions. That it's very like very simple exercise. We wanted to make it very simple. So we just compute responses to monetary policy shock using like very typical sign restrictions. So what you see here is the response of PCE inflation. This kind of purple, I guess, line is the inverse Wishart model, and the other lines, these greenish lines, dash, dotted, etc., are the different orderings. No, and you see, for instance, at the trough here, there are really some differences. No, this is quarter and this is not annualized. So if you annualize it, these are really big differences of like 0.4. Similar for the unemployment rate, even bigger. No, you see that the inverse Wishart is kind of reasonable, more or less in the middle, but you see that not for the entire buffer, but you also see that different orderings give really different IRFs. Not in terms of shape, but in terms of the magnitude. And these numbers are big. No, this is unemployment rate. So if you would accumulate this, this gives you quite a big difference in the unemployment rate response to monetary policy shock in this setup. Let me conclude. So there are differences in both reduced form and structural results depending on the ordering of variables. The autographic inverse Wishart specification does not suffer from this ordering problem and provides plausible structural results and comparable forecasts. This PGAS, which is the particle gives with ancestor sampling, has not been used so frequently. It has been used, but not much. And as I said, we will make Druya code available. And what's work in progress is we're doing the same exercise for the euro area data. Sorry, for just euro, the euro area. And we're working on a replication of a published paper that does some structural exercise using a model with the stochastic volatility. And we want to show that when you change the ordering in this paper, the ordering of the variables in this paper, you really get different results. Okay, this is work in progress, and hopefully after our summer holidays we will finish it. Okay, well, thanks for your attention, and I'm happy to take any questions. If I have time.
Question one, maybe, yeah, super interesting. Thanks. I think we got of intuition on your approach. So I was thinking, imagine you take a standard Primi-Cherry approach, right? And you do different ordering. In one case, you have large differences. In the other case, you have very small differences. Does it have an impact on your approach?
So What do you mean on our approach?
So what does it mean? I don't know, does it have an effect on your specification on the approach? Or, I mean, we have an intuition that if results are more or less similar,
Yeah.
in that case, our approach is likely to provide also similar results, right?
Ah.
And while if you have very large differences after the delivery, maybe your approach to do something different or to do that. I don't know.
So we didn't invest.
Just an intuition.
No, I would not have any intuition. We didn't try to investigate this yet by looking at how if bigger differences between the year.
Because I think that your approach could be useful in case there are large differences, right?
Between orders.
In case there is no.
Yeah, but we didn't. So far, we didn't look at this, but maybe we can think about if there's any pattern to be found.
Maybe by simulation.
Yeah.
Based on data.
Yeah. Yeah. Okay. Thanks. Yeah, we can look at it. Yeah. Yeah. Thanks.
Okay, perfect. So then, thank you, Florence. I'm going to Lucas.
You already opened it. Okay, thank you very much, everybody, for coming. Thank you to the ISF, the Macroeconomic section, and Greg for inviting and accepting this paper into the conference. This is joint work with Adam Lee and Gerd Meesters, who are both at Pompeu Fabra at the moment in Barcelona, and it's titled Robust Inference in Structured VAR Models Identified by Non-Gaussianity. And so in this paper, we look at the standard k-dimensional structured VAR model, which we have written here in this notation where the A inverse matrix captures the contemporaneous structural impacts of the structural shocks epsilon. And we have here a version of the model which assumes that the structural shocks themselves are IID over time. So it's very well known. This is kind of the classical identification problem in this literature that based on first and second moments of the data, we cannot pin down this A inverse matrix fully. We need to impose structural restrictions. And depending on which structural restrictions the literature adopts, there are big discussions on the plausibilities of these. And most of these are inherently untestable. However, in recent years, there has been a lot of attention to a literature that points out that if we exploit higher moments of the data, so third order, fourth order, or cumulants in general, then we can use this to shrink the identified set for this A inverse matrix without having to impose additional structural restrictions. Now, such an approach is obviously very attractive because it essentially avoids big discussion on which structural restrictions are plausible. And so the typical approach that is followed here in the literature is that you make what's called the ICA assumption. So this is called ICA because it comes from the independent component analysis literature, which originated in the signal processing literature dating back to this paper by Coleman in 1994. So essentially, the typical approach goes as follows. You assume that the individual components of the structural shock vector, epsilon kt, are independent from each other, and that at least k minus one of these follow a non-Gaussian distribution. And if you have that, then you can show that you get statistical identification of this A inverse matrix up to sign and permutation of columns. So if you think about the structural IRFs, if you're able to label the structural shocks and maybe impose some additional sign restrictions, then you don't have to impose any additional theoretical restrictions, and you essentially get identification from non-Gaussianity or from higher moments. Now, because this is so attractive, a lot of recent works have started to exploit this approach in practice, applying it to all sorts of different applications. And then essentially any additional theoretical restrictions become over-identifying. So you can then essentially try to test the restrictions that have been discussed previously. Now, however, as we point out in this paper, this is not a free lunch, essentially. So this method has some important potential drawbacks. And some of these have been pointed out already in the literature, in simulation studies, but we highlight them here specifically, and then we also provide a solution to that. So the biggest problem here is that this approach can suffer from what we would coin weak non-Gaussianity identification, so weak non-Gaussianity identification problem. And the intuition is as follows. So if you assume that these structural shocks are non-Gaussian there's a whole range of different degrees of non-Gaussianity that these shocks could have. And if these shocks indeed are somewhat closer to a Gaussian distribution, then it turns out that standard inference in the structure VRR is no longer valid, and you get size distortions if you test hypotheses on this A inverse matrix, or coverage distortions if you try to construct bands for the structural impulse responses. And so the intuition behind this is essentially just another weak identification problem, right? So in the IV problem, we sort of need a sufficient correlation between the instrument and the autonomous regressor. Here, we need a sufficient distance from Gaussianity in order for standard asymptotics to kick in and inference to be valid. So what we do in this paper is we show that you can indeed conduct inference under weak non-Gaussianity based on an approach that relies on the efficient score function of this model. And we show that this inference remains valid both in the case where you have weak non-Gaussianity or in the case where you actually have Gaussianity, which then comes at the cost that power of this approach is essentially flat. So particularly what we do in this paper is the following steps. We first show that you can use a semi-parametric generalization of Neyman's C alpha statistic to test these possibly weakly identified parameters. And the approach remains valid and the test control size, even if the data would indeed be Gaussian. And then building on that, we propose a method to construct confidence sets for any smooth structural functions. So here, the most popular things to look at would be IRFs or forecast error variance decompositions, using the proposed test statistic in combination with the Bonferroni based procedure. And we show that this has correct coverage regardless of the level of non-Gaussianity in the structural shocks. Then we have a big simulation study where we look at the final sample performance of this method. So size, power of the tests, coverage of the impulse response bands. And then finally, we revisit some of the empirical applications that people have looked at in recent years using non-Gaussianity identification, such as the Baumeister and Hamilton simple labor supply demand model and the oil price model of Killian Murphy 212. So before I go into the details of the approach, maybe let's have a very quick look at a very simple structure VAR and try to understand a little bit better sort of how does this non-Gaussianity work? What could be the issue with weak non-Gaussianity? So for this, similar to what we saw in the last presentation, I'm going to ignore all of the legs in the structure VAR. So I set P equal to 0. Then we essentially just get a structure VAR model where the shocks have a contemporaneous impact on the variables. And I'm also going to make an additional assumption that this A inverse matrix, this mixing matrix, is orthonormal. Now, this can be asymptotically satisfied by pre-whitening the data essentially beforehand, so it's without loss of generality. Now, what's nice about this setup is that if we have a bivariate structure VAR, then we can express this A inverse matrix as a rotation matrix. And now we have one scalar parameter, which is this alpha, which determines the impact of the structure shocks. So if alpha is equal to 0, then A inverse is simply the identity matrix. So every shock just affects its own variable. But depending on the angle of alpha, which goes between 0 and 2 pi or multiples thereof, you get sort of different rotations of this orthonormal matrix. Now, what's very nice with this is that we can now look at the expected log likelihood of this model for different distributions for these structure shocks. And this is what I show you here in the picture. So first, have a look at the top left panel. This is essentially illustrating the standard identification result in the structure VAR literature. So here, we assume that the density of the structural shocks is just a normal 0, 1 or a T infinity in this case. And we can see that the likelihood is completely flat over this rotational angle. So this just reflects the standard problem that under Gaussianity, we need additional restrictions because the data is not informative of all of the parameters in the A inverse matrix. Now, if you look on the other diagonal where we have a T5 distribution, so sort of somewhat stronger non-Gaussianity, then indeed we can suddenly see that based on the data, we can actually start to pin down this parameter alpha. And you see this kind of sign-based pattern that just comes from the fact that if you change the columns, if you permute the columns and flip the signs of the structural shocks, for every of these permutations and sign changes, you get the same kind of likelihood shape. Yeah? But really, we have statistical identification here of the parameter up to permutation and sign changes. Now, what we look at in this paper are kind of the intermediate cases, which you see on the off diagonal. And as you can already see, when you go from T5 to T10 to T15 towards Gaussianity, you see this log likelihood, expected log likelihood becoming flatter and flatter and flatter. And this is sort of the sense of weak non-Gaussianity, the weak identification problem essentially that we get here. The closer we are to Gaussianity, the less informative the data is about these structural parameters. So how can we solve this problem? So what we do is we borrow from the semi-parametric literature and we combine their insights with this weak identification robust testing literature. And we first cast the structured ER as a semi-parametric model. So here you see the structured ER where all of the lags have been sort of summarized in this xt variable. B is just your standard sort of lag polynomial on this. And then A inverse is actually the contemporaneous impact matrix that we're interested in. We split the parameters here into 3 groups. We have alpha, which is the potentially weakly or unidentified parameter. So in the illustration I just showed you, this is just this one scalar parameter. And then we have beta, which are the strongly identified Euclidean nuisance parameters. So this involves the lag parameters, but as well as variances, the variance part, which is the sigma part here of this A inverse matrix. So these can typically be recovered from second moments of the data. And then we have a third part, and this forms the non-parametric part of the model. And that is this eta parameter, which captures the infinite dimensional nuisance parameter. So essentially the densities of all of the structure shocks. Now, as I said before, here in this model, you can still recover B by OLS, for example, or by GMM. And then given a value of A, the model is suddenly identified, and sigma can be recovered from the variance of YT, either by a Koleski decomposition, depending on the structure you impose on A inverse, or by a method of moments approach. So now how can we actually use this to conduct valid inference on this alpha parameters? So we have 2 approaches in the paper. One is for doing a valid test on this alpha parameter, which governs the structure impact matrix. And the second is for constructing impulse response bands. So the procedure kind of goes as follows. You start by estimating the reduced form parameters, which are here beta hat, and then you recover residuals from the model. Then based on the residuals and a hypothesis on alpha, which is alpha 0, you can then recover sort of your estimate of the structure shocks, and you can use this to compute the log density scores of the model. What we do here is we avoid making a parametric assumption to say, okay, we assume this non-Gaussian density, but what we do specifically is we use a sort of B-spline approximation, so a non-parametric approximation directly of these log density scores. So then we have log density scores evaluated at these estimated structure shocks. What we then do is we remove this infinite dimensional nuisance parameters by projecting these log density scores onto the space that is orthogonal to the space that's spanned by this infinite dimensional nuisance parameter. And then we do another projection where we remove all of the reduced form parameters so that in the end, we're just left with an efficient score that is only for the alpha part. And then we use that and we simply form sort of the equivalent of a Neyman-C alpha statistic, which you can see here. So we just have the typical LM form here. And I here is a pseudo inverse, a Moore-Penrose pseudo inverse of the information matrix, which you can construct as the outer product of the score. So we construct the statistic. This is computationally really convenient because essentially just for every hypothesis you make on alpha, you just have to do this B-spline approximation, which is essentially just a linear projection problem. And you compute this test statistic, and then you reject if the test statistic is bigger than a critical value, which comes from a chi-squared distribution, where the degrees of freedom is simply equal to the rank of this estimated information matrix. So to form confidence sets, what we do is we typically invert this test over grid. So we set up a grid of different hypotheses for alpha 0. We run the test for any of these, and we only accept the values for which the test does not reject. And then we look at the union of this to form a confidence interval for alpha. Okay, the second approach that we have in the paper is then how can we use this to construct valid inference on any smooth function of this weakly identified parameter alpha and the strongly identified parameter beta. And so the way that we do this is we have some function g where we have a Jacobian j of gamma. So this could, for example, be the IRF or the forecast error variance decomposition. And j gamma here just denotes then the derivative with respect to these parameters. So we first do everything I just told you on the last slide. So we obtain a confidence set for this alpha parameter. And then for every value in this confidence set, we estimate the reduced form parameters of the VAR and the covariance matrix of these parameters. And then we can essentially apply asymptotic delta method with a Bonferroni correction where we have Q1 and Q2. Q1 is the critical, like the level that you use to construct the confidence set for alpha. Q2 is the level that you use to construct for every point in the confidence interval for alpha, this asymptotic delta method band. And then we simply look at the union as those for the confidence band. Okay, now we're doing on time. Okay, perfect. So I will just quickly talk about some simulation results, and I will show you one of the empirical applications. So what you can see on this table is just the size of this first stage test. So this is the semi-parametric score test. And we have here a comparison with other alternative approaches that have been used in this non-Gaussianity identification literature. So the first two rows you see, the S at OLS and S at one step, is our test statistic using two different estimates for the nuisance parameters. And what you can see on the column are all these different distributions that we look at for the structure shocks. And you can see that our test statistic, our test has a size of roughly close to the nominal size, which is 5% here, regardless of which distribution of the structure shocks you impose. But all of the competing methods, some of them are supposed to be more robust to a non-Gaussianity, some of them not, have this issue that eventually they run into some severe over-rejection under the norm. And we also look at power, and we find that for all these different distributions, power remains very high with our approach. So it's typically competitive with the other alternative methods that exist in the literature, and sometimes even outperforms them. And you can see that sort of the more non-Gaussianity you have, the higher the power of this test is. And then finally, we look at coverage and average length of the confidence bands for the impulse response functions that we construct. So here what you can see is the average length for the IRF of the first variable to the first shock when we construct the confidence bands using our method. So this is the black and the red line versus one of the competing approaches, which is by Drausburg and Wright, where they have a GMM-based procedure. So that's sort of imposing some, using some higher order moments to estimate this, or one which is based on an independence test that they have. And you can see that overall, the average length of our confidence intervals is very similar, and sometimes we even get much shorter confidence length. And this is all while being computationally more convenient, because approaches like the Drausburg and Wright approach essentially involve doing a bootstrap for every point in this grid over which have to invert the test statistic. Okay, so this leaves me a couple of minutes to very briefly talk about one of the empirical applications. So in the paper, we have a couple of them, but I just wanted to highlight one here, and that is the Baumeister and Hamilton bivariate US labor market example. So in this model, Baumeister and Hamilton, they have a structure VAR with 8 legs, where they have a supply elasticity parameter and a demand elasticity parameter, which is the alpha S and alpha D. So we treat these as the potentially weakly identified or unidentified parameters, and then all of the other variance parameters can be recovered from the data itself. Now, this application was recently revisited actually by Lan and Lotto, who have a GMM-based inference approach under non-Gaussianity, and they criticized one of the restrictions that Baumeister and Hamilton put on this model, namely one of the long run restrictions that they put in place on the effect of labor demand shocks. So we revisit this model without imposing any sort of assumptions on either non-Gaussianity or any of these long run restrictions, simply based on the sign restrictions that Baumeister and Hamilton impose, that the short-run wage elasticity of demand is negative and the supply elasticity is positive. And then we can use this first stage test to construct joint confidence regions for the supply and elasticity parameters. And what you can really see here is that for high values of the supply elasticity, this demand elasticity parameter is reasonably well identified, but overall, the data itself on the model cannot distinguish between either having a very negative large elasticity of demand parameter and a very small supply elasticity parameter, or having very large elasticity of supply parameter and very small elasticity of demand parameter in magnitude. And then when we construct confidence bands for the impulse response functions, this naturally translates into a similar result. So we get quite wide bands, which are sort of comparable to the bands you would get simply by imposing signing restrictions. They're just shrunk a little bit. But most importantly, if you take a look at the effect of the demand shock, you can see that for long horizons, we cannot rule out that the impact of the demand shocks is 0 at a 90% level here. So that means the criticism of saying that these restrictions are not plausible, at least based on non-Gaussianity and the data alone, we cannot rule that out. Yep, and that's really it. So we have the semi-parameter statistic, which we use to conduct valid inference in the structured VAR setup under potential non-Gaussianity. I've shown you that the size of this test is close to the nominal size, and power remains typically large. And then we have this test inversion plus Bonferroni way of doing valid inference on the structured IRFs. And then we have several applications where I showed you that non-Gaussianity identification might not be sufficient to really pin down the economy's response in this labor supply and demand model by Baumeister and Hand. Thank you very much.
Thank you, Lucas. I believe the one we have maybe in the break. Okay, perfect. All right. Let me see if the screen is being shared. No. Okay. Perfect. Thank you so much. My name is Greg Anich, and I'm very happy to be here with you. And I'm going to talk about constructing the term structure of uncertainty from the ragged edge of SPF forecasts. So this is joint work with Todd Clark and Elmar Mertens, and of course the usual disclaimer applies. So these are our views and not necessarily those of our employers. Okay. So the research agenda for this paper is the following. So imagine the following setup that we face. We observe predictions from the Survey of Professional Forecasters or similar sources of macroeconomic surveys in the form of point and density forecasts at fixed horizons and or fixed events. And the problem that we are solving in this paper is constructing fan charts, that is term structures of expectations and uncertainty, which are consistent with the Survey of Professional Forecasters. Namely, we are filling in the missing values and we fit forecasts from a model onto the SPF, onto the Survey of Professional Forecasters without resorting to using measurement error between the model and the Survey of Professional Forecasters. Namely, we take those point forecasts from the Survey of Professional Forecasters literally, and our model is able, as I will show you, is able to exactly replicate, to exactly fit those points and fill out the necessary points, which are not as in the Survey of Professional Forecasters. In this paper, we have a state space model which maps the Survey of Professional Forecasters point forecasts into predictive densities for the outcomes at fixed horizons. And it builds heavily on earlier work by my co-authors, Clark, Mertens, and McCracken. In other words, CMM, which relied on the observed fixed horizon forecast errors. Our assumption for the DGP that drives the outcomes is a fairly agnostic one. Namely, we just assume an 8-step ahead wall decomposition, and we treat the long-run forecasts as martingales. Let me emphasize again that our approach is able to match arbitrary term structures of expectations that we can see in the data. And then in the next step, what we do is that we match the SPF histograms using entropic tilting, which I'm going to briefly introduce later on. And here we replicate the entire bin structure. So we take the probabilities assigned to bins, these histograms in the survey, without having to estimate moments which is, quite frequently done in the literature. So as for related literature, here there's a very long list that in the interest of time, I would skip. Basically, what you can see here is that we are trying to connect our paper. We're trying to speak a large audience, in different fields of forecasting, and with dealing with the survey forecast as well. So let me just talk about the agenda. So I'm going to talk about the survey of professional forecasters data. Then I'm going to summarize the state-space model that is at the heart of our approach. And then I'm going to introduce entropic tilting as sort of like a second step method. And then I'm going to talk about the effects of entropic tilting on the predictive densities and illustrate our approach here. So what we do is that in this paper, we limit attention to the forecast of the average respondent. So we are not dealing with the dispersion or the disagreement between forecasters. We sort of take the average respondent as the SPF forecaster, and then we observe point forecasts, as I told you, between quarters 0 to 4. So between the nowcast horizon up to 4 quarters out. These are the fixed horizon for point forecast. We also observe point forecasts for calendar years, from the current calendar years to 3 years out. These are the so-called fixed event point forecasts. What we do is that we ignore the current year predictions because these are spanned by the quarterly point forecasts. And then we also observe density forecasts, which are fixed event forecasts for the current calendar year and 3 years out. But we only consider these histograms from 1992 onwards due to data issues. And again, we ignore the current calendar year predictions. The availability of these point forecasts and these histograms differs across time and across variables. So this is sort of a difficulty that we need to take into account. Today, I'm going to focus only on the real GDP growth results. The rest of the results for the unemployment rate and for the GDP deflator are in the paper, and we are very happy to share them with you. Okay, so we are going to show how to model densities around the point forecast, which are given in the survey of professional forecasters. In this step, we are going to estimate models which are able to sort of interpolate between the point forecasts that were given in the survey of professional forecasters, being centered on the point forecast that were given in the survey. And then in the next step, we are going to use the information contained in the bins, in the histograms, and we let the models match the probabilities given in the SPF bins. Okay, so the state space model, which is at the heart of our approach, is basically an unobserved components model with stochastic volatility. So here, what you can see is the first equation is the observation equation. Namely, what we do there is that we map the observed outcomes and point forecasts, which are contained in this ZT vector. We are matching them, we are mapping them into this partially latent vector YT, which contains the fixed horizon forecasts. Now, what is important is that this C matrix, which does this mapping, is a deterministic matrix, which is given by the data definitions. I'm going to talk about that in a moment. And then there's the state equation, which is the second equation in the slide, which is basically just an accounting identity for forecast errors. And then how we specify this eta vector, which is the vector of forecast updates. This is going to be, a decision that we need to make. In the baseline case, we treat this as a martingale difference sequence. In an alternative case, understanding that there are papers which have demonstrated that SPF forecasts are not necessarily rational, namely forecast updates are serially correlated. We can also treat them as a persistent process, namely as a VAR1 process. In our empirical application, we don't see big differences. And then, of course, we can specify either stochastic volatility for this eta vector or treat the variance of this as a constant. And I'm going to talk about these choices in a moment. So remember that I told you that this CT matrix is a deterministic matrix. Basically, the idea is that we are using this tent-shaped approximation for for constructing annual average levels and growth rates based on the quarter-on-quarter growth rates. So this is what you see in the first formula, and for the unemployment. So this applies for the real GDP growth and for the GDP deflator. And for the unemployment rate, we're just taking the average of the quarterly levels to get the annual level. So as I told you, the CT matrix does not require any sort of estimation. This is literally just a deterministic matrix mapping the establishing the mapping between the annual growth rates or the annual levels with the fixed horizon or the fixed events and the quarter-on-quarter growth rates or the quarterly levels of the variables. Okay. Next, the accounting identity that I mentioned. So basically, the idea here is that we can write we can use forecast errors and forecast updates to get predictions. Namely, we can write the nowcast error as ET, YT minus YT given T, and then we can write the H step ahead forecast error as well. This is this ET T plus H, and namely we can decompose this. We can literally, this is just an identity. This is the H step ahead realization and the H step ahead nowcast. Okay, the difference of this is the H step ahead nowcast error and the sum of the forecast updates. This is what you see in the second term on the right hand side. And we can just denote these forecast updates by mu T plus H given T, which is the change in the point forecast going from period T minus 1 to T. Okay, and this idea was used by CMM to sort of map fixed horizon forecast to generate fixed horizon forecasts at other horizons, but they relied on the observation of these fixed horizon forecasts and fixed horizon forecast updates. Now, as I told you, we have the state space for the fixed event forecast as well. Namely, what we can do is that we can take again this 8 step ahead, this identity, this accounting identity, 8 steps ahead. This capital H corresponds to the longest horizon involved in the survey of professional forecasters that was actually recorded. And then what we can also do is that we can track the changes in the long horizon, in the long run forecast. And then there's this mu T star, which is basically the change in the point forecast for the longest horizon, going from one period to the next. Okay. And basically, if you put all these together, then you get a state equation with a known transition matrix F. Okay, so this transition matrix is again going to be known, no estimation needed there. And then in this eta T, as I told you, we are collecting all these forecast updates and of course the last periods nowcast error. Okay, so this is the idea. This closes the state space model for the forecasts. As I told you, the baseline approach that we take is that the forecast updates are unpredictable, so we treat them as a martingale difference sequence. In other words, we are not trying to out forecast the SPF. So the posterior densities are going to be centered on the point forecast given by the SPF. And then in terms of variance a specification for this eta for the forecast updates, we either specify that as having a stochastic volatility or having a constant variance specification. As an alternative, as I told you, we can also treat these forecast updates following a low order VAR process. We do not get significantly different results with that choice either. Okay. So let me just talk about the estimation setup. We estimate the model separately for each outcome variable. Here I'm only going to talk about real GDP growth. We use MCMC over growing samples using real-time data and the survey of professional forecasters conducted by the Philadelphia Fed. And then we generate out-of-sample predictive density starting in 1992 Q1 onwards, and then we evaluate our forecast against the second release of the outcomes. Okay, so remember I told you that we can perfectly match any shape of the term structure of expectations. So in terms of point forecast that you can see in the data. And here, let me just show you an example. So here the red diamonds are the quarterly SPF forecast for real GDP growth. Okay, and then the gray line that is labeled as SV model goes through these points by construction, and then the quarterly growth rates, the annualized quarterly growth rates, you can see, and the corresponding bands you can see after the last horizon for which there is an SPF point forecast. And these dotted lines correspond to the annual growth rates that were given in the SPF. These are also mechanically matched by our model. The reason why you see not just four quarter long lines is because I told you that there is this tent shaped approximation, this log linear approximation that is used to match, to sort of convert this into a linear problem. Okay, so this is what you can see here in 2009 Q2. We can also compare our stochastic volatility results in terms of 68% predictive bands from the stochastic volatility model to the survey, to the SCP that was used by the FOMC. So this is, here you can see that basically these fan charts based on historical forecast errors assume constant variances, but the stochastic volatility approach is able to more closely track the sort of the volatility that you see in the economy. So in terms of the stochastic volatility decreased after the great financial crisis, while the SCP bands remained elevated. Okay, so entropic tilting, just very briefly, basically here, this is how we match probabilities from the histograms. And how we turn probabilities into moments that we are able to match with this entropic tilting. Basically, this entropic tilting is about reweighting the MCMC draws subject to the new draws, sorry, the reweighted draws obeying the moment conditions, here namely the probabilities, while staying as close as possible to the original density in terms of the Kalbach-Leinberg divergence. So the real takeaway, let me just show you this. In terms of density forecast evaluation, the entropic tilting does not add much to the results that we already have, and also neither in terms of point forecast. This is because the model's predictive densities are already centered around the SPF point forecast. In terms of COVID, entropic tilting did help by narrowing the bands at the onset. This is not really surprising. This is consistent with stochastic qualitative model doing a good job. And then here, let me just leave the conclusions here. So we propose a state space model that can match arbitrary term structures of expectations, then we can incorporate the information, the additional information in the SPF bins via entropic tilting. We see that forecast uncertainty varies considerably over time. Histograms do add some value, but not consistently, although at the onset of the COVID crisis, they did. And that's all I wanted to say. Thanks a lot for your attention.
I saw one graph that one forecast for which the confidence bands are decreasing over time.
This one?
Yeah.
Okay. Right. So here, what you also need to see is that there's information, in this 3-year ahead SPF forecast, and that information is able to actually shrink, the bands potentially, because the predicted distribution need to obey that its mean has to be the same. So it's not like there is only information at the 4 quarters out, but the model uses information also at longer horizons. And of course, if from 15 onwards we would show you the bands, those would of course keep increasing. But here it's not true that as you go for higher horizons, the bands would necessarily widen.
So go in the same direction.
No, it's not because of that. It's because so here the predictive bands also incorporate information at from the 3-year ahead SPF. Okay, so that's why there is this potentially it could also widen, but it doesn't have to widen. But that's the longest horizon at which we use information from. So I'll be happy to explain that in the yes.
These are bands for the mean or for the
yes. So these are the bands for the mean. Yes, for the point forecast. That's right. No, the entire distribution. The entire distribution, for example, is this. Okay, that's only for the point forecast. Exactly. Okay. Yes, please, Lauren. Yes. Okay. So that's a very good question. So as a matter of fact, we do see. So of course, then the bias is sort of baked into the results, or at least we are not treating the SPF forecast as unbiased. The results, I believe I have them here. I can. No. Yes, exactly. Here's the bias. Exactly. So here you can see the bias. At different horizons. Okay, from the non-MDS model. So the case when we treat the SPF forecast as potentially biased, you see that there are very, very small biases. Basically, of course, the COVID period is sort of the big outlier. In other terms, there's really not much to be gained from treating the SPF forecast as potentially biased. They do check, yeah. So of course, also in this one, in this figure. So maybe if we need to go, I'll be very happy to show this to you. With the horizon, as the horizon increases, there's more and more bias. Clearly, yes, absolutely. Yeah.
In one of the first slides, you showed was there some linear approximation to the angle?
Correct. Yeah. This is the yes, exactly. This is the typical Mariano and Murasawa approximation. This is how you I sort of translated an inherently nonlinear problem in using a log linear approximation into the, the sum of the quarterly growth rates. Yeah. Okay, perfect. Well, thank you so much. And I would like to thank everyone for coming. And please don't forget that Felix is a student, so you can vote for his presentation. Thank you so much, everyone.